Okay, after we prove the sum law, scalar coefficient law, the product law, and the quotient law for the limit, we can determine the limit of certain complex functions. For example, let's see, find the limit approaching infinity n cubed plus n squared minus 1 over 1 minus 3 n cubed. Okay, so, oops. Okay, good, now it's better. Okay, so first of all those terms except a constant term have no limit. The limit does not exist for most of the terms. So we cannot apply any law directly. So what we do is the following. We are going to divide the top and the bottom by the highest power. So among all these terms, the highest power is n cubed. So we divide every term by n cubed. N cubed over n cubed is 1. N squared over n cubed is 1 over n. 1 over n cubed is 1 over n cubed. 1 over n cubed is 1 over n cubed. 3n cubed over n cubed is a 3. Okay, so that's the first step. We divide the top and bottom by the highest power among all these terms. And then we see that the limit of 1 over n is 0 at infinity. 1 over n cubed has limit 0 at infinity. And this has limit 0 at infinity. So the numerator becomes, the limit of numerator becomes 1 plus 0 minus 0 is 1. The denominator has a limit 0 minus 3 is 0. So we apply the quotient rule plus sum rule plus scalar coefficient rule. So directly get the, we get this limit. So first, one thing I want to remind, in the list of the previous theorem, we only have the sum, scalar coefficient, product, and quotient. We only have those four. But in fact, we also have the difference rule. What is the difference rule? Remember that when we have xn minus yn, we can consider it as a xn plus the negative yn, right? And the negative is the coefficient alpha equal to -1. So we apply the coefficient rule. We have the difference rule. So difference rule is a combination of a sum rule with a scalar coefficient rule. Okay, so later we can directly apply the so-called the difference rule. We don't have to always say it is a combination of a sum rule with a coefficient. All right, so that's the remark. We have addition, subtraction, scalar multiplication, multiple, product, and quotient. And also the product rule can be combined with this the coefficient rule can be combined with the product rule. You just consider xn as alpha, the constant function. So this is a special case of the product rule. So this is a special case of the product. One of the factor is just constant. Okay, so that's a special case. Okay, so we have the list of those rules. And now let's talk about another stuff. You see, The sequence of n, of course, it diverges, divergent. And the sequence of -1 to n times n, also divergent. But those two divergent sequences are different. They diverge differently. So what is a divergent differently? N, the sequence of n, it has one direction. It just go higher and higher. But the sequence -1 to n times n, it go up, down, up, down, up, down, this way. It's jumping. It's jumping. So it does not approach any point. It does not approach any point. Here, it approaches bigger and bigger position. Okay? They are both divergent. Why this is divergent? Because it's not bounded. Right? Remember that convergent sequence must be bounded. This is not bounded, so it's definitely divergent. Here is also divergent. But even though among those two divergent sequences, we want to tell the difference. This one, it does not approach any position, but this one, it has one direction. It will approach there. But that position is not a number. Okay, so we want to give a name for this type of a divergent situation. Okay, it has a direction to go. This one has no direction to go, it's jumping. Okay, so that's the next definition, definition 2.14. So let xn be a sequence of real numbers. Okay. Xn is said to diverge to past infinity if and only if for each m in R, whatever m, every m, there is in capital N in the natural numbers such that when the index n is greater than or equal to capital N, you will get xn is greater than m. Okay, so that's what we call the diverge to past infinity. You can put plus sign or you just ignore the plus sign. So here this capital M, it says for each m in R. But in your mind, you should understand this m as bigger as possible. Right? When m is 10, you have a integer, a natural number n, so that after that position, all the terms are greater than 10. When m is 1,000,000, you have another natural numbers, so that after that position, remember this little n represented index, first, second, third terms. After that term, all the numbers in the tail will be greater than this m. So m will be understood as higher, bigger and bigger. Okay, so that's why we use it to describe past infinity, because past infinity will be greater than whatever pre-selected capital M. Okay. So this is the first part, and the second part xn is set to diverge to negative infinity. So negative infinity, you have to put a negative sign. If and only if for each m in R, there is a capital N in the natural numbers such that n greater than or equal to capital N implies xn is less than m. So here, this m, because it represents negative infinity, this m will be understood as small as possible, negatively large. Right? It can be understood as negative meaning. After capital N, all the terms will be less than negative meaning. After capital N, all the terms will be less than negative meaning. So that's a representation of negative infinity. Negative infinity is less than whatever pre-selected negative numbers. Okay? Okay. So in the short sentence or in the intuitive idea, it says, okay, this is a complete definition. We have divergent to positive infinity and divergent to negative infinity. In the intuitive way, it says xn approaches positive infinity if and only if xn is greater than or equal to m for sufficiently for any m in R, x is greater than or equal to m for sufficiently large n, and xn approaches negative infinity if and only if for any m in R, xn is less than or equal to m for sufficiently large n. So this condition, there exists the capital N. It is the precise writing for the sufficiently for this word. All right. So remember that when we have the when we have the calculus, we define the limit. We just say sufficiently close, sufficiently. So this is sufficiently. Okay. With this definition, divergent to infinity or negative infinity, we will have the similar theorem like the square theorem and like the sum and difference rule. Okay? So, theorem 2.15. Suppose that xn and yn are real sequences such that xn approaches infinity positive as n approaches infinity. Okay, so we only know one sequence approach positive infinity. We only know one. Then first, if yn is bounded below, then the limit n approaches infinity, xn plus yn is still infinity. Okay, so that's a statement. Part of the that's a statement for the part one. And here we have the counterpart. This is the situation when x approaches positive infinity. If this part you assume xn approaches negative infinity as n approaches infinity. Okay, so this is replaced by the negative infinity. Then this bounded below should be replaced by bounded above. Okay, so bounded below is replaced by bounded above. Then this conclusion is replaced by xn plus yn is negative infinity. It does not change this negative limit. All right. And second, if, okay, so x approaches past infinity. If alpha is positive, then the limit n approaches infinity, alpha times xn. When xn approaches positive infinity, so eventually it becomes a positive number. So eventually alpha times xn is still a positive number. So this is positive infinity. Okay, x approaches in positive infinity, you get a positive infinity. If in this sequence, if in this situation, if xn approaches negative infinity, alpha positive, alpha is always positive. Alpha is positive, then the limit n approaches infinity, alpha xn will diverge to negative infinity. So for whatever situation, alpha has to be positive. We only multiply this divergent sequence by a positive coefficient. Okay. You see, this is sum rule, coefficient rule, product rule. What is a product rule? If yn is greater than m0 for some m0 positive and all n. Okay, so this one, you see, alpha plays a role like the yn. So we require all the yn to be positive, and also it is bounded below. Positive and bounded below. Then the limit n approaches infinity, xn yn is still positive infinity. It diverges to positive infinity. And this part, we have the parallel way. If xn originally diverges to negative infinity, then the limit n approaches infinity, xn yn, it will be negative infinity. Okay, so I always write this parallel case in the parentheses so that you can see that all the statement in the parentheses are the result for the divergence to negative infinity. All right, and the quotient rule. The quotient rule, if yn is bounded, and xn is not equal to 0. Whenever you see xn is not equal to 0, it means we are going to place it on the denominator. Then the limit n approaches infinity, yn over x will be 0. Yn over x will be 0. In this place, even though you assume this you assume xn approaches negative infinity, it is still 0. Here. It doesn't matter xn approaches positive infinity or negative infinity. If you place it in the denominator and the numerator is a bounded sequence, then this quotient is always 0. All right. In the book, the author proved the case when xn approaches positive infinity. Well, let's prove the other part when xn approaches negative infinity. You read the proof for the positive infinity. See if we can match them. We assume that xn approaches negative infinity as n approaches infinity. Okay, we're trying to prove all the statement in the parentheses. Okay, so part 1. Y is bounded above. Yn is bounded above. Bounded above means there is in capital M such that Yn is less than or equal to capital M for all n. For all n, right? Okay, so let's see. We're going to show xn plus yn still approaches negative infinity. Now let's see. Xn approaches negative infinity as n approaches infinity. It means, by the definition, that for any let's release this. Let's use a different word, a different L. Let's use L. I want M here. For any M in R, this is L. The upper bound is called L. For any M in R, there is a natural number n such that xn is going to be less than m. But this time, let's subtract L. M minus L is still arbitrary number, right? M minus L. Okay, then for n greater than or equal to capital N. Then what do you get? For the same, then for n greater than or equal to capital N, xn plus yn is less than m minus L, and plus L is m. All right? So for any m, there is a capital N, so that for n greater than capital N, xn plus yn is less than m. By the definition, the limit approaches infinity, xn plus yn is still negative infinity. It diverges to negative infinity. Okay, so you can see that actually this is just a counterpart of the proof you can read from the textbook. It does not surprise a lot. Okay, so this is part 1. Part 2, we are going to show, oh, okay, where's part 2? Part 2 is here. We are going to show the coefficient rule. Coefficient rule. Well, first of all, let's still copy this. Xn approaches negative infinity as n approaches infinity. It means that for any m in R, there is a capital N in the natural numbers such that xn is less than whatever for n greater than or equal to capital N. Remember, because there's a coefficient, so we put m over alpha. M over alpha. Okay. Okay, so now alpha is positive. We apply the multiplication by alpha on two sides. So alpha xn is less than alpha times m over alpha is m for n greater than or equal to capital N. Okay, so for any m, there is a capital N such that for n greater than capital N, alpha xn is less than m. See, that's exactly the definition of a divergence to negative infinity. So by the definition, the sequence x alpha xn approaches negative infinity. And the important thing for this alpha, positive alpha, is that when you multiply two sides of the inequality by alpha, you still preserve the direction. So this place you use the positivity of alpha. And this proof does not work for the negative alpha. Okay? The proof does not work for the negative alpha. Actually, negative alpha will switch positive infinity and negative infinity. All right? And 3, what is the 3? 3 means, okay. 3 is, okay, we want the negative case. We want the negative case. Negative case negative case. Let's see how do we do the negative case here. Again, let's copy it, and then we will see what it is. Xn approaches negative infinity as n approaches infinity. It means, I repeatedly copied because I want you to memorize this process, memorize this definition for any m greater than m in R. There is a natural number n in N such that xn is less than m. Well, let's leave it. Less than m for n greater than or equal to capital N. But here, you remember, you're going to multiply it by. You're going to multiply it by what it is. By yn. Okay, so we put m over m0. Check here. This is m0 in the assumption of a third part. If we only leave it like this, then check here. We will have problem. The problem is the following. When we do the multiplication, okay, so it's not done. It's not done. Let's see the analysis. Here, there's a small difference between the positive infinity and negative infinity. Positive infinity, you read it from textbook. You just, for the positive infinity, it's greater than yn. If it's a positive infinity, it's this case. Then you multiply xn, yn is greater than this yn over m0 times m. Then everything will be solved. It's greater than m, so it's checked. But this is in the book for positive infinity. But for our negative infinity, we have a problem, because if we do it, we cannot do the multiplication, because this is negative, this is less than or equal to. Here is greater than or equal to. We want to do this product without additional condition. We have no conclusion. All right, so there's no conclusion for us now. Since there's no conclusion, let's emphasize. Let's try to add something. Remember that this xn will approach negative infinity. So eventually, it is a negative number. Okay, so eventually, it is going to be a negative number. Okay, so for the negative number, we assume For the negative number, we're going to do the following assumption. Here, we assume that this capital M is negative, and it suffices to prove the theorem only for negative real number. Why we say that only it's sufficient to prove the theorem only for negative real numbers? Because it's less than. If you have a positive m, you're looking for n, for the capital N. So you just try to find a negative 1, and you find the capital N. Then the xn will be less than negative 1 for all n all n greater than or equal to capital N. And negative 1 will be definitely less than m. So for the same n, the xn will be less than capital M for n greater than or equal to capital N. The same thing. So you only need to prove some smaller number. Then for all the real positive numbers, positive m's, this capital N will work. Okay, so that's why we can assume m negative and go through the proof. Okay, so now m is negative. M is negative, xn becomes negative. M0 is positive, so the quotient is negative. So yn xn is less than or equal to m0 xn. Okay, less than or equal to m0 xn, because this comes from the multiplication of an inequality, this inequality by a negative number. So you see here, we do change the direction. Originally has no equal sign. Let's skip the equal sign. Okay, and then from here, you're going to use this this inequality. This inequality you multiply it by m0. It's a positive number, so you preserve the inequality. All right, so here you change the direction because you multiply this inequality by xn, a negative number. Here you still keep this direction because you multiply by a positive number, m0. Okay, so xn yn will be less than m if n is greater than capital N. All right, hence by the definition, the limit n approaches infinity, xn yn will be negative infinity. Okay, so this place, to assume the negativity of xn is crucial. You have to understand this part, because remember that when it approaches negative infinity, almost all the terms will be eventually negative. When you have negative terms, do this product, you're going to change the direction. But if you only consider the original situation for any m, then you cannot get xn negative. So you have to strongly assume m is negative. All right. So this is the difference. Okay. Okay, now let's see the part 4. Part 4, we are going to show the limit is 0. The part 4, okay, part 4 is here. Part 4, the numerator is bounded, the denominator diverges to negative infinity. Okay, we'll prove the limit is 0. It's a real number, it's a concrete number, so we have to use epsilon capital N language. So let epsilon be greater than 0. First, choose m0 such that yn ops value is bounded by m0. Okay, so this is one thing. Let's see what's next. What is next? Okay. So again, remember we are going to use this. For epsilon, choose m negative with what? With m0 over negative m is less than epsilon. Okay. We choose a negative number so that m0 over negative m is a positive number. This becomes harder. So that the ratio is less than epsilon. Okay. Then for this m, for this selected m, there is a capital N in N such that for all n greater than or equal to capital N, where xn is totally less than or equal to m. Remember, it's negative. Okay, so that's the situation. Now let's see the conclusion. The conclusion will appear. So we are going to show yn over xn minus 0 less than epsilon. So this is the opposite value of yn xn. Yn opposite value is less than m, so it's less than m0 over xn. Okay, so this is xn is negative, so it's m0 over negative xn. Opposite value of xn is negative xn. Negative xn am I making a mistake? Let me see. Okay, now let's see. Do I make mistake? No, I'm not. Okay, so xn is less than or equal to m less than 0. So negative xn is greater than or equal to negative m is greater than 0. But when you flip them, 1 over xn less than or equal to 1 over negative m is still greater than 0. Okay, so we still have the less than. So it's less than or equal to m0 over negative m. And this is less than epsilon. See? Okay, very good. I don't make a mistake here. Okay, so for every epsilon, you find the m. From m, you get capital N. So from epsilon, there is a capital N. When n is greater than or equal to capital N, opposite value of the difference is less than epsilon. So by the definition, the limit n approaches infinity, xn over yn is 0. Okay, so that's the proof. You check the textbook, they will give you the similar proof. The textbook provided the proof for the positive infinity. Here we try to get the proof for the negative infinity part. All right. Okay, so to make those, this is the addition, subtraction, multiplication, division, the rules for the infinity. If we want to write those rules in the simple way, it's the following. We will write every number plus infinity is infinity. Every number minus infinity is a negative infinity. So here, when we say every number, it means whatever number, positive, negative, or 0. So this works for all r. Okay, add infinity. Whenever we don't put a negative sign, it's always positive infinity. Add infinity is always infinity. Subtract infinity is always negative infinity. If you do multiplication, a number, this part you have to say this is positive number. A positive number times infinity is infinity. A positive number times negative infinity is negative infinity. Here, x has to be positive. And if you get a negative number, multiplication with negative number, you're going to change positive infinity to negative infinity, and the negative infinity to positive infinity for a negative number. Okay? For negative number, you exchange positive and negative infinities. For positive number, you preserve positive and negative infinity. And we also get the positive infinity plus positive infinity is positive infinity. And the negative infinity minus infinity is still negative infinity. All right? And other product will be that positive infinity times positive infinity is still positive, and the negative infinity times negative infinity is also positive, and the positive infinity times negative infinity is negative infinity times positive infinity is equal to negative infinity. All these symbols should be understood as a limit process because we don't have infinity. Whenever you see infinity, it is realized by certain sequence or the functions stuff. All right? So especially be careful about this part. And also you see here in the second part, the scalar coefficient alpha x positive, x negative, x cannot be 0. If x is 0, remember that indeterminate form. 0 times infinity is indeterminate. Indeterminate. Remember that. So you have the L'Hopital's rule stuff that very complex. So don't have this. And also for the quotient infinity over infinity, it is indeterminate. And the infinity minus infinity is indeterminate. Right? So this part excluded from this list. This is determinate. This is indeterminate. All right. Next, if we want to combine the case for the concrete number and the infinity, we have the following corollary. The corollary is the following. Let xn, yn be real sequences. And alpha, x, y be extended real numbers. Extended real numbers means we include the plus minus infinity. All the real numbers plus positive and negative infinity. If xn approaches x and yn approaches y as n approaches infinity, then you see n always approaches positive infinity because n becomes bigger and bigger, greater and greater, is always positive. So this part there's no negative infinity. Then the limit n approaches positive infinity, xn yn is x plus y is equal to x plus y. Of course, this part exclude infinity minus infinity. So this case, you cannot let x be positive infinity, y be negative infinity. That one is excluded. That is excluded. So indeterminate form. And also the limit of alpha times xn is alpha times x, and the limit xn yn is equal to xy. And this part exclude 0 times infinity. 0 times infinity. This is in the plus minus case. This is in the product case. All right? And actually this is in the quotient case, but it's not in the corollary, so we don't mention it. So when you have alpha equal to 0, xn approaches infinity. That one is always 0. Here, when xn approaches 0, yn approaches infinity, then this limit is indeterminate. So this is corresponding to that. Okay, when alpha is 0, alpha times xn is always 0, so the limit of 0 is always 0. Even though xn approaches infinity, this part is always 0. So we don't discuss the case when alpha is equal to 0. So here, see, if alpha is equal to 0, then alpha times xn is always 0. All the xn's are real numbers. Here, when we say alpha x, y to be extended real numbers, alpha, we don't consider it as infinity. When we say extended, we mean x and y are extended real numbers. All right, so you will never say alpha times xn, infinity times xn. That's not the regular case. Okay. Okay. So anyway, when you do the limit laws, make sure you keep alert about indeterminate form, infinity minus infinity, 0 times infinity, and infinity over infinity. You need the L'Hopital's rule. Okay, so next we have the so-called the comparison theorem. The comparison theorem is an extension of the square theorem. Square theorem, you have 3 functions: left, right, and middle. Left or right controls the middle term. In comparison theorem, you only have left and right. Okay, so suppose that xn and yn are convergent sequence A's if there is an n sub 0 in the set of natural numbers such that 1 xn is always less than or equal to yn for n greater than or equal to n0. So for sufficiently large n, they have this relation. Then what you can say is the following: the limit of xn should be less than or equal to the limit of yn. You cannot get equality because you only have one way. Okay. Okay, and in particular, if xn belongs to A and B, converges to C. If you have a sequence in the closed interval, it converges to C, then C belongs to AB. So closed interval will contain its limit point. So that's what it means. Closed interval will contain the limit point. Okay, so let's see the proof. Suppose the statement is false. The statement is false means the limit is greater than 1. Then the limit of xn equal to x strictly greater than the limit of yn equal to y. Okay? So this is strictly greater than y. Okay, so this is y, this is x. Then what you can have, then let epsilon be what? Be 1/2 y minus x. If we don't want 1/2, we can put 1/4. We can put 1/4. Okay, so this is 4 times of epsilon. X minus y is the distance between y and x. divided by 4, so we divide this distance into 4 parts, so the distance is 4 epsilon. Okay, for epsilon, there is n capital N greater than 0, a capital N belong to the natural numbers, such that for n greater than or equal to capital N, what we have? We have xn minus x less than epsilon, yn minus y less than epsilon. So this means xn minus x is less than epsilon, is between negative and positive epsilon. Yn minus y is between negative and positive epsilon. In other words, we add y for 3 positions, we will get xn is bounded by x minus epsilon, x plus epsilon. Yn, same way, is bounded by y plus epsilon, y minus epsilon. Okay, so let's see the geometry. This is 4 times. This is epsilon, and this is x minus epsilon, x plus epsilon, y minus epsilon, y plus epsilon. See, so eventually xn is greater than x minus epsilon. X minus epsilon is here. X minus epsilon is greater than y minus epsilon. Y plus epsilon is greater than y plus epsilon. Here's y plus epsilon. Here's x minus epsilon. It's because of this setting. Okay, and this is greater than yn for n greater than or equal to n. Well, this contradicts to the situation. The situation says eventually xn is less than or equal to yn, but here we say eventually xn is greater than yn. Contradiction. This contradiction tells us so the limit of xn must be less than or equal to the limit of yn. Again, it tells us eventually the element of the sequence will be very close to its limit. If the limit is bigger than that, eventually this the element of xn will be greater than the element of yn. Okay. Okay, so that's a contradiction, and that's a proof of the first part. And the second part is simple because xn is bounded by an and bn. So the limit by the first part, the limit of xn is bounded by a and b because they are constant sequence. The constant sequence has a limit itself. So c is between a and b. Okay, so that's not the serious case. Okay, so we get this comparison test, comparison theorem. Okay, so let me see what kind of exercise we need to practice. Okay, so on page 44, you can try the problem 3. Problem 3, I almost finished it, but I skipped some part because of the time. 5, and 6, okay, let's just leave 3 exercise. Okay, anytime if you have a question, just feel free to send me email. We can try to discuss it. Okay, thank you very much.